Something quiet became something dangerous in a single step. At a distance of just over 2.1 astronomical units, the interstellar visitor we call 3I Atlas suddenly began releasing hydrogen cyanide into space. If comets are supposed to warm up slowly, why did this one flip on like a switch? Stay with us. You and I are going to walk straight into the paradox. Classical comet behavior is a ramp, not a cliff. As sunlight increases, ice is warm and vapor lift begins. First water, then carbon monoxide, then other volatiles. Brightness grows, a coma forms, a graceful tail streams away from the sunday. It is a slow sunrise, not a light bulb. 3I Atlas did not follow the sunrise. In mid-September, the James Clerk Maxwell Telescope reported hydrogen cyanide emission at a distance near 2.13 astronomical units. The confidence level was described as beyond 5 sigma, which in human words means the odds of a false positive are tiny, far less than 1 in a million. The measured production rate was on the order of 4 times 10 to the 25th molecules every second. That is a number so large it blurs into feeling, but we can ground it. In the time it takes to breathe, this object throws off more cyanide molecules than there are grains of sand on every beach on Earth. Let us translate cyanide without drama. Hydrogen cyanide is a simple molecule that blocks the last step of cellular energy production. In high concentration, it is deadly. In space, it is also perfectly ordinary. Many comets carry it, locked in their ices, released as they warm. So the presence of cyanide is not the shock. The timing is the shock. Weeks earlier, the same telescope looked for this exact molecule at the same radio frequency bands and saw nothing. Flat spectra, quiet skies. Then, at nearly the same instrumental setup, a clear signature appeared as if someone, somewhere, opened a valve. So, what changed? Distance alone should not do this in a single step. Solar. Heating increases gradually along the orbit. Sublimation tends to scale with that heating. Even messy, unpredictable comets tend to announce themselves with hints before a surge. Dust lifting. Faint lines. Small brightenings. Here, the first real sign is a switch. That is our puzzle. We will test the most generous natural story first. Maybe the nucleus is a patchwork of materials with very different thresholds. Perhaps sunlight finally reached a seam or a pocket. A crust cracked. Volatiles that had been sealed found a path to vacuum and erupted. Comets fragment. They spin. They hide complexity under dull skins. That is true. If this is the answer, other signals should follow. A change in brightness that correlates with rotation period. Dust shells expanding in waves. Repeated on and off pulses as the active spot turns into and out of sunlight. Natural messiness has fingerprints. Now the bolder question. Could this be an engineered threshold? Not a geological crack, but an internal rule. Wake at this distance. Vent at this rate. Use a specific molecule because the system inside prefers it, or because it makes a clean exhaust. It sounds wild. It also fits the observation in a single sentence. A device can wait. Then it can turn on. We do not need faith to compare these models. We need measurements and patience. If this is natural, we should watch a curve, not a staircase. The output should scale with heat. The gas mix should evolve in a way typical for comets. If this is artificial, we should watch for discontinuities and directionality, plumes that behave like jets rather than a uniform fog, subtle nudges in the trajectory that are hard to blame on sunlight alone, small non-gravitational accelerations that persist beyond what outgassing usually produces. The sky keeps score. There is a second paradox riding next to the first. The hydrogen cyanide output is enormous, yet 3I Atlas remains faint compared with the great comets you know from photographs. Where is all the dust that makes comets bright? Where is the textbook tale? If the emissions are mostly gas with little dust, that is unusual. If a veil of charged particles is masking some of the light, that is a different game entirely. We will come back to that. For now, hold the feeling that two things are true at once. Strong gas signal, modest glow. This is not a courtroom. It is a laboratory in the open. We will keep the numbers in plain speech. We will keep the chemistry human. We will avoid jargon for its own sake and only deploy terms that help you see the object with your own mind. When we speculate, we will say so. When we can calculate, we will. The goal is not to win an argument. The goal is to understand what is actually passing through our neighborhood and how it truly behaves as the sun's grip tightens. So here is our working map. 3I Atlas crosses a quiet threshold near 2 astronomical units, and begins releasing hydrogen cyanide at a rate that shakes the imagination. Classical comet physics says that should be gradual. The data says it was abrupt. The next weeks decide which story survives. If this is the dawn of ordinary cometary activity, we will watch the slow light. If this is a device waking up, the next steps will look like decisions. Stay close. We have a switch to explain. Rewind the tape. Late summer, the same observatory points at the same patch of sky with the same frequency settings and sees nothing. Flat spectra. No hydrogen cyanide line. No whisper of unusual activity. Then we jump a few weeks. Mid-September. Identical setup. Same sky. Same instrument chain. Now, the line blazes into being. It is as if the universe waited for a cue we did not hear and then shouted. So what truly separates those two nights? Distance changes, yes, but only a little. Heating rises, yes, but gradually. Comets usually answer that kind of nudge with a slope. A little more sunlight leads to a little more vapor. Dust drifts off. The coma thickens. Over days, not minutes. You watch the curve lift and you nod because nature loves gradients. Here, the curve looks like a stair. Let us hold on to the control surfaces we can trust. Instrument parity means we are not comparing apples to oranges. The radio bands are the same. The calibration steps are the same. The reduction pipeline is the same. We cannot blame the flip on a different knob setting. That matters because the mind tries to escape any paradox by inventing a hidden knob. In this case, the knobs seem fixed. So we turn to the body of the object itself. Imagine a crust of dark, compacted dust over ice. Sunlight works on it day after day. Microfractures spider slowly through the cover. Volatile pockets strain. Somewhere inside, pressure builds. Then one fracture links to another, and a path to vacuum opens. Release. The cometary version of a champagne cork. In this natural crack model, the timing would be set by internal structure, rather than gentle external heating. That can make an eruption feel sudden even though the stress took weeks to accumulate. If that is what happened, we should expect follow-through. Rotational modulation because the active patch turns into and out of the light. A periodic heartbeat in the outgassing rate. Dust shells moving outward like ripples on a pond. Now consider the threshold model that lives one step to the side of geology. Not a cork, a timer. A dormant device that wakes when the sun is a certain size in the sky. 2.1 astronomical units is not magical. It is simply a clean reference that a designer might encode. Wake here, run diagnostics. Vent at a controlled rate. From the outside, that would look exactly like a switch. The question is whether anything else lines up with control. Directional plumes. Persistent non-gravitational acceleration that tracks the vent geometry rather than the rotation. On-off cycling that does not match day and night on the surface. Those are signatures of decisions, not fractures. Our timeline lets us test both ideas. Late August to early September gives us the quiet baseline. Mid-September gives us the step. Everything after that is the ground truth of how the system behaves under load. If the natural crack story is right, the outgassing should settle into a thermal relationship with distance and rotation. If the threshold story is right, we may see second switches as other subsystems light up in sequence. Not a ramp, but a staircase with landings. There is also a small but nagging detail. In the quiet weeks, the spectra were clean across the searched bands. No weak shoulders, no hints just below the noise floor that later bloom into a line. That lack of a prelude is unusual. Many comets tease you with a faint line that grows. This one gave us silence followed by certainty. If instruments were to blame, we would expect random blips at other times. We do not see them. Silence, then signal. That rhythm keeps pointing away from noise and toward physics. Where does that leave us as viewers who cannot tweak a telescope from home? With a set of simple checks. Does the cyanide line scale smoothly as the object approaches the sunday? Do other molecules appear in the standard order for comets as the temperature rises? Do light curves show periodicity tied to rotation? Do dust features expand in predictable arcs? If yes, the crack model gains weight. If not, we return to the notion of internal control, and we look harder for thrust like geometry in the plumes. One more frame helps make sense of the step. Think of a frozen lake in early spring. The first warm day does not melt it. Stresses build invisibly. Sound travels through the ice as pings and low rumbles. Then a loud report splits the quiet as the sheet shifts and a lead opens. You can call that sudden. You can still call it natural. The crucial difference here is auditability. Ice on a lake leaves lines you can walk across and measure. A faint interstellar object leaves only the light it gives us. That is why this timeline matters. Repeated null results, followed by a high-confidence detection under identical conditions, is a rare clean experiment in the wild, the sky itself controlled for us. We will keep both candidates on the whiteboard. Pressure release in a complex nucleus that happened to reach its tipping point near 2.1 astronomical units, or an internal threshold chosen by design that simply uses that distance as a trigger. The next acts will tell us which story has to work too hard to stay alive. Curves prefer the natural tail. Steps prefer the engineered one. Our job is to trace the shape with care and refuse to look away when it contradicts our favourite ending. Picture a mountain that sleeps without a puff of steam or a tremor of warning. Then, on a cool morning, it erupts in a single clean burst. No foreshocks, no small plumes. Just a switch from nothing to something. That is the feeling of 3I Atlas at 2.1 astronomical units. The chart looks less like sunrise and more like an instant noon. Comet chemistry usually follows a familiar sequence. As sunlight rises, the surface layers warm. The gentlest volatile is often water, which begins to sublimate and drag dust grains away from the nucleus. Carbon monoxide and carbon dioxide show up with their own signatures. Other compounds follow as deeper ice warms or fresh layers are exposed by erosion. It is a staggered procession. A parade that enters the square one band at a time. With 3I Atlas, the band we heard first was hydrogen cyanide, and it marched in suddenly. How could that be natural? Start with the most grounded idea. The nucleus is not a smooth snowball. It is a quilt of hard crust, porous pockets, and veins of frozen gas. Over weeks, microcracks spread under thermal stress. Pressure builds behind a patch that serves as a lid. At some moment, a crack network links a pocket to the vacuum of space. The pocket vents. Gas rushes out, dragging a little dust. The release is abrupt because the path went from closed to open in one breath. On a light curve, it reads like a step. On the sky, it looks like a fresh jet from a specific latitude and longitude on a tumbling body. Natural eruption leaves natural signatures. If the new vent sits off the rotation axis, we should see the output wax and wane with the spin as the spot turns into sunlight, then into shadow. If dust is present, we should see shells or spirals that expand and thin with distance from the nucleus. If the pocket feeds on nearby ices, we should see the gas mix evolve as the vent chews sideways into different layers. The eruption model predicts texture. It predicts a rhythm tied to the day and night of the comet itself. Now, step across an invisible line into a different kind of volcano, not a trapped pocket, a designed chamber. Imagine a dormant probe that carries internal stores and uses a chemical like hydrogen cyanide as part of a startup routine or as the exhaust of a safe mode thruster. It sleeps through deep space for ages. Then it measures the sun's brightness, calculates distance, and at a programmed threshold powers on. Valves open, pumps spin, gas vents through ports that aim in chosen directions. From the outside, the event is the same light on our spectrograph. The difference is intent. One case is fracture, the other is a decision. How would we tell those apart at a distance? Direction is the first clue. Natural outgassing spray is messy and follows the surface. Designed plumes favour clean, repeatable angles that do not care about small-scale terrain. Timing is the second clue. Natural vents ride the rotation unless there are many of them. Designed plumes can hold steady through a full spin or fire in pulses, unrelated to day and night on the surface. Momentum is the third clue. All vents push, but a device could tune thrust to create a small, persistent, non-gravitational acceleration that grows measurable over days and weeks and aligns with plume, geometry, rather than the changing orientation of a lumpy nucleus. The volcano in the sky image helps for one more reason. It corrects our intuition about danger. The eruption is impressive, but it does not mean doom by itself. Space is vast. Gas expands and thins quickly. Hydrogen cyanide in the void is a tracer, not a death cloud, unless it is coordinated in time and aimed with care. So the question is not only what came out, but how and why. There is also the quiet question of dust. Comets get bright because sunlight bounces off dust grains that the gas lifts away from the surface. If 3I Atlas releases a river of gas with little dust, it will look dimmer than the chemistry suggests. That could be the nature of the material. It could be a crust that resists scouring. Or it could be something else entirely, like a halo of charged particles shaped by magnetic fields that masks light and muddles spectra. If the mountain wears a veil of plasma, we would misread the eruption through that veil. We will test this in a later chapter when we talk about plasma sheaths and stealth. For now, we stay with the image that got us here, a sleeping mountain that wakes without a tremor. If it is natural, the crack model asks us to look for rotation-linked pulse and dust geometry. If it is engineered, the chamber model asks us to look for clean angles, steady thrust like nudges, and gas timing that ignores the surface day. The next observations are the seismographs we cannot put on the mountain. Our instruments are the ground under our feet, and the light is the rumble we feel through it. So what if it is not a camera trick? What if the stair-step is the thing, not the artifact? Then we are standing at the lip of a caldera in the sky, waiting to hear whether it will cough again, louder and cleaner, as the sun grows larger and the power budget increases. If this is a volcano of nature, it will settle into a rhythm we know. If this is a volcano of design, the next cough will sound like a... Start with what should have been a gift, a spacecraft with eyes in deep space, instruments tuned, a geometry window that put 3i Atlas in reach. If there were ever a chance to catch clean images and spectra from a vantage point beyond Earth, that first week of September was it. Then, the record goes quiet. Public archives show a gap across the exact days when the alignment was best. No routine calibrations, no housekeeping frames, just absence where there should be footprints. Silence has innocent explanations. Spacecraft sleep, teams push software updates, instruments cool, the deep space network points away for relay windows. Sometimes, a computer hiccup triggers safe mode and non-essential systems power down until engineers can verify health. Data can also bottleneck in processing. Pipelines delay uploads until calibration is confirmed. All of that happens in real missions. Boring reality is often the right answer, yet this quiet arrives wrapped around the ideal observation window. Before the gap, the object is approaching. During the gap, it is closest from that perspective. After the gap, it is already on the way out and beginning to change chemically. Silence that lands on either side of a moment like that invites questions. Was this timing mundane bad luck, or a pause that protected data that did not fit the public frame? We do not need to jump to villains to feel the pinch. Anomalies create headaches for mission teams. If an instrument captured something unexpected, it would go through internal verification before any public release. Teams would check pointing, thermal conditions, detector stability, clock sync. They would compare against engineering logs to rule out artifacts. If surprise survived all of that, the next step might involve quiet calls to partner agencies and security desks. Not because someone wants to hide the universe, but because novel data carries reputational and policy risk. People move slow when the stakes are unclear. Let us walk the timeline the way an archivist would. In mid to late August, routine postings tick into the public catalogue as the spacecraft cruises and tests systems. Then, the first days of September show nothing, not a trickle of thumbnails, not even the dusty corners of an engineering folder. After the 7th, entries resume, healthy cadence. That sandwich of silence becomes part of the story, even if the real cause was a simple maintenance window with poor luck. The sky does not wait for our meetings. The cleanest path forward would be a plain note from the team, a dated line that says, "We paused instruments for a planned reset," or "We lost contact for a day or two and recovered." Even a "we" are still processing that week, and will post when ready would diffuse the narrative pressure. Instead, we have absence, and a community already charged by the poison switch and the strange tail geometry. In that mood, even ordinary gaps read like redactions. There is a more delicate possibility. Suppose the spacecraft did take frames, and the automated first pass flagged a pattern that looked engineered. Sharp edges, where a natural coma should blur, jets from fixed points that repeat with clock-like precision rather than surface rotation, a faint shape hinting at panels or ports. A team that saw that would not post before checking and rechecking. They would not risk a viral mislabel that collapses under a week of scrutiny. They would put the images through every sanity check they have, and then some. Time would pass, and the public archive would remain blank until a decision was made. We can also build the natural mirror to that story. Suppose the instruments were down for something prosaic, a software patch, a power cycling sequence, a reaction wheel momentum dump that required a different pointing mode. In that case, the week is a coincidence. The absence is real, but the cause is boring. The problem is that the sky does not annotate coincidences for us. The narrative vacuum fills with speculation faster than any pipeline can clear a backlog. What would change the temperature right now? 2 simple artifacts would help. First, a short engineering note that lists the health state of the instruments for that week even without images. Second, a commitment to release either the missing data or a justification for why no data was collected. Neither requires taking a stance on the nature of 3i Atlas. Both would lower the room's blood pressure. Transparency is cheap compared with the cost of spiraling mistrust. There is a practical reason this matters beyond drama. The exact window of that silence overlapped the best opportunity to see surface or coma structure that ground-based telescopes cannot resolve. If there were any physical changes tied to the onset of hydrogen cyanide release, the before and after of that week would have stitched a clearer story. A clean sequence of frames could have shown whether vents formed at specific locations or whether the glow simply thickened everywhere at once. That lost comparison is why this gap keeps ringing. So where do we place this puzzle piece? Not as proof of a cover-up, not as evidence of incompetence. As a reminder that the chain from photons to public understanding has many links, and a single weak link can distort the whole rope. We will keep looking for simple explanations and for posted updates. We will also admit what the gap does to the intuition. When you want to look the most and the window is dark, the mind leaps. Part of discipline is naming that leap and then asking for receipts. Until those receipts arrive, we log the week as a missing page in the field notebook. We will not write our ending in that margin. We will mark it and move on to the next line of evidence, because one silence does not get to carry the entire story. Patterns do. If the pattern repeats across different instruments and agencies, then the silence speaks louder. If it does not, this moment will shrink to the die, size of an odd annoyance on the way to an answer. Start with the rule, every beginner learns. A comet's tail points away from the Sunday always. Solar wind is a river of charged particles that streams outward from the star. Sunlight adds a gentle push called radiation pressure. Gas and dust feel those forces and are swept downstream, so no matter which way a comet travels, the tail points away from the furnace. Now look at the photographs and reports that put grit in that tidy rule. 3i Atlas showed a narrow feature that at times extended toward the Sunday. The word for this is anti-tail. It sounds like a paradox, but sometimes geometry plays tricks. Imagine dust not being blown away immediately. Imagine it settling into the comet's orbital plane like a thin sheet. From Earth, if we happen to look along that plane, the sheet can line up with our line of sight. Part of it will appear to point sunward, even though each grain is still obeying the push of the Sunday. That is the normal explanation, and in many cases it is right. So why did this one bother the people who have seen many anti-tails before? 2 reasons: persistence and prominence. Anti-tails are usually brief and delicate. They appear when viewing angles are just so, then fade as the geometry shifts. With 3i Atlas, observers described a feature that held on longer than the easy story expects and stood out more boldly than the typical faint hairline. Add in nights when the object looks strangely bare, then nights with sudden puffs and angled jets, and the picture stops behaving like a single neat projection effect. Let us teach the physics in plain words. A comet really has 2 tails, an ion tail made of gas that gets electrified and carried by the solar wind, and a dust tail made of tiny grains kicked off the surface by the gas. The ion tail is the obedient one. It follows the wind and snaps like a streamer in a gale. The dust tail is lazier and curves gently because grains have inertia and sunlight pressure is weaker than the wind on ions. An anti-tail is not a third tail. It is a visual trick where the dust sheet is seen edge-on and looks like a spike toward the Sunday. The trick depends on timing and viewpoint. Here is the test that any non-trick has to pass. If a sunward feature is purely geometric, its brightness and length should track our angle to the comet's orbital plane. As that angle changes, the feature should fade predictably. It should also stay narrow and smooth because it is made from old dust left in the orbital track, not fresh jets. If the sunward feature is fed by active vents, we should see ripples and knots that line up with rotation or with specific source points on the nucleus. One is a fossil footprint. The other is a living hose. What did people report with 3i Atlas? Intermittent puffs, jet-like spikes at odd angles, a coma that would swell and then seem to relax. Some nights a modest tail, other nights a bare point. Nothing about that screams a single sheet of antique dust seen just right. It sounds like a body with hot spots that turn on and off, and sometimes point in directions that make the simple classroom rule feel wrong. There is a natural path through this thicket. Suppose the nucleus is rotating with 1 or 2 active vents near the poles. Then gas jets could project almost sunward at certain rotations, because the geometry between the spin axis, the sun, and our viewpoint lines up to create that impression. Add a sprinkling of charged dust that interacts with magnetic fields, and you have a recipe for briefly misbehaving structures. This cocktail can produce quirks without invoking anything engineered. There is also the directional exhaust idea whispering from the edge. If a device is using jets for attitude control, the plumes point where they must, not where physics of sublimation would prefer. That can create sharp features that ignore the smooth curves of a natural dust tail. It can also invert expectations. A jet aimed partly toward the sun could carve a sunward spike while still being knocked back by the wind at larger distances. Up close, it looks wrong. Farther out, the wind reasserts loyalty and drags everything away again. Which story fits best? That depends on how the feature evolves with time and angle. The antidote to confusion is choreography. Watch the length and brightness of the sunward spike as the comet and Earth move. If it behaves like a projection trick, it should follow the math of the viewing angle and fade on schedule. If it is driven by vents, we should catch repeating pulses tied to rotation. If it is something more deliberate, we might see steadier plumes at fixed angles, less concerned with the day and night of the surface, and more concerned with maintaining orientation. There is one more clue hidden in colour. Ion tails and dust tails glow differently because they scatter and emit light in different ways. A simple spectroscopic look can separate a charged gas feature from a dust sheet. If the sunward spike shares the ion signature, the projection story weakens. If it looks like dust, the case for geometry strengthens. If it looks like neither cleanly, we are back to the possibility of a plasma veil that distorts everything we see. So ask the simple question that keeps this honest. Could this all be a cosmic coincidence? Or is something else going on? If we can explain the sunward feature with a plane of old dust seen from a perfect angle, that is the clean win. If the feature stays too bold, lasts too long, and carries the fingerprints of live jets, then the rule has an exception that needs a better cause. 3i Atlas is teaching class whether it wants to or not. Our job is to pass the test without pretending the questions are easier than they are. Sometimes, the problem is not what you see, it is what you are told to wait for. As 3i Atlas swept past the orbit of Mars, 2 orbiters had a front row seat with instruments built read the fingerprints of gas. We expected quick spectra, even if rough. Instead, we got applause shots, distant dots, a press line that said detailed analysis would take months. Months is not a scandal by itself. Spectroscopy is careful work, but the timing scrapes the nerves when the story already feels off. Let us translate the promise into simple steps. A spectrometer spreads light into a barcode of wavelengths. Certain molecules leave crisp marks in that barcode. Teams calibrate the instrument, subtract backgrounds, and match lines to known patterns. When everything behaves, a first look can be shared quickly. Later, deeper studies refine numbers and ratios. We have seen this cadence before. Methane hints at Mars came out fast in the past. Water vapor maps followed at a human tempo. Here, the pace is glacial right, as the audience watches an active visitor do strange things. Why might that be normal? Calibration may be rough when the target is a small, faint source. The orbiters were built to look down at a planet, not track a point in deep space. Signal to noise may be poor. The teams may want to stack multiple passes to beat the noise before saying anything. They may also be juggling mission priorities. An orbiter that hunts trace gases on Mars cannot stop being a Mars mission just because a comet swings by. None of that is sinister. It is the daily life of spacecraft. Still, the public pattern matters. Fuzzy images now, specific molecules later. The human brain fills empty timelines with stories. If those stories already include a silent week from a different mission and a sunward tail that refuses to behave, then the delay looks like a lockbox. Put the good stuff behind a door and promise to bring it out after the season finale. There is a cleaner way to handle a moment like this, and it does not require breaking process. Share the plan in plain words. Tell people the bandwidth budget for comet observations. Tell them how many passes are in the queue. Tell them the thresholds you require before you label a line as real. That kind of transparency lowers the noise without revealing any secrets. It also gives the audience a fair yardstick. If a promised date slides, everyone knows why and how far. What could the spectra reveal that makes teams so careful? The obvious is the mix of gases. Water, carbon monoxide, carbon dioxide, hydrogen cyanide. Ratios matter. Temperatures matter. If the mix is weird for the distance, that is news, even if the cause is natural. Isotopic ratios are the spicier layer. The weight of atoms tells a story about where and how material formed. If those ratios look deeply unlike the comets we know, the paper writes itself and the press release drafts are eager to go live. Unless the ratios look like nothing we have a natural story for yet. Then caution rules. There is another possibility that reads like science fiction until you put your thumb on the physics. A thin plasma veil around the object could scramble the light in ways that confuse classification. Ionized gas can bend and smear spectral lines. If the orbiters saw a barcode that shifted shape between passes, teams would hesitate. You do not publish a label that moves around. You wait. You test. You look for stable features that survive the scramble. That takes time, and from the outside it looks like a locked drawer. None of this argues for a grand design to hide the sky. It argues for a design flaw in how we talk about delay, when anxiety is already high. Space science has a trust budget, as real as any fuel budget. Spend it well and the audience will carry you through hard patches. Spend it poorly, and every routine hiccup becomes a plot point for someone else. Here is what to watch while we wait. If first-look spectra appear soon, and they show a normal ladder of molecules that brightens toward the sun, the natural story gets a tailwind. If the lines are skewed toward exotic molecules, or if isotopic ratios push into unfamiliar territory, then the case for unusual chemistry grows. If the teams publish a clear timeline and hit it, the narrative calms. If the timeline keeps moving without explanation, the lockbox metaphor will harden into belief whether it is true or not. We should also remember that the best answer is often dull, a noisy data set, a team stretched across too many tasks, a priority call to stay focused on the planet they were built to study. But dull does not excuse silence. When the world is watching an object that may rewrite a chapter of planetary science, announcement discipline becomes part of the science. Speak a little sooner. Teach a little more. Do not let a blank page write a louder story than the spectrum will. 3i Atlas has already burned one switch in our minds. The Mars orbiters can help decide whether that switch belongs to geology or to design. The sooner we can see even a rough barcode of its breadth, the sooner speculation can give way to reasoning. Until then, the lockbox stays a symbol, not a verdict. The door can open with a single plot of light versus wavelength, and a voice that says, "Here is what we know today, and here is what we do not." That is how you keep a public investigation honest. That is how you keep a mystery from owning the room. So what if this is not a frozen rock with a bad temper? What if it is a device that knows where the sun is and waits for a distance written into its bones? The question is not whether that sounds wild. The question is whether the behavior we can measure fits a device better than a dirty snowball. Tonight we place the two stories side by side and refuse to let either hide behind poetry. Start with what an engineered traveler would need. A dormant mode that lasts for ages with almost no energy drain. A wake trigger that does not depend on a clock that can drift, but on a reference that never lies. The apparent size of the sun at a certain distance is a perfect trigger. Wake at 2.1 astronomical units. Run. Checks. Vent to clear lines. Warm internal tanks. Spin up guidance. From the outside, that would look like a switch. Right where the record shows a switch, a device would also need control. Gas makes thrust when it leaves a nozzle. Even a whisper of thrust adds up if you keep it steady for days. That thrust would not care about which patch of surface is in sunlight. It would care about where the nozzle points. So we look for direction. Plumes with clean angles that repeat. Features that hold their pose through a full spin of the body. Small nudges in the orbit that line up with those angles instead of the shifting day-night pattern. That is, exhaust 101 written across the sky. Now the natural mirror. Comets crack. They tumble. Their vents wake and sleep as the body rotates. A single hotspot can imitate a nozzle for a while if it sits near a pole or finds shade and sun in a tidy rhythm. Outgassing can produce non-gravitational acceleration too. It is not a privilege of machines. The question is not whether thrust can happen. It is whether the thrust obeys geology or guidance. Bring in the chemistry. Hydrogen cyanide is not a smoking gun for design. It lives inside many natural comets, but the sequence and the rate matter. If the first big breath is cyanide, and the dust stays low, that is a weird recipe for a natural surface near 2 astronomical units. If other gases appear later in the classical order, as the object warms, the natural story grows stronger. If instead the gas mix stays skewed while activity pulses on a schedule that does not track rotation, the device story takes a step forward. Energy is the other pillar. Near perihelion, the power budget climbs fast. Solar panels, if they exist, would surge. Thermal gradients would grow. A machine that needed to do anything ambitious would wait for that surge. So we watch for phase changes that begin not just because the sun is closer, but because a system crosses a chosen threshold. 2 thresholds in one season would be the telltale shape of a plan. Wake at the outer line, act at the inner line. There is a quieter test you can run at home with a notebook. Plot nightly reports of brightness and tail shape against the predicted rotation period. If you see a heartbeat tied to spin, you are looking at vents on a body. If you see a second rhythm that holds steady while the spin goes by, you may be watching control. Machines love steady beats, rocks love messy syncopation. Consider the geometry of the so-called anti-tail. A projection trick can make dust look sunward for a short time when we stare along the orbital plane. A nozzle can make a sunward spike on demand until the solar wind drags it down. If the spike keeps its attitude while our viewing angle changes, that is a mark in the device column. If it comes and goes with the geometry, the natural story wins that round. We should also talk about silence, not as a conspiracy, but as an operating mode. A cautious probe would keep emissions low until it needed them, because emissions are signatures. A faint object that shows strong gas lines but stubbornly modest dust could be a traveller that minimizes reflectivity on purpose and activates dust only when the job requires it. That sounds like science fiction until you remember that minimal signatures are standard in every engineered vehicle class we build. The principle scales. So where does this leave a sane mind? With a short list of falsifiable signs, directional plumes that hold steady through rotation, small but persistent changes in velocity that align with those plumes, gas timing that prefers thresholds over slopes, a perihelion action that looks like a second switch rather than a hot afternoon. If the sky delivers those, the device idea earns more than a shrug. If the sky delivers rotation-linked puffing, a normal ladder of gases, and a tail that obeys the math of geometry, the rock wins. Could this all be a cosmic coincidence? A pile of ordinary effects landing in the same month to fool us? Yes, coincidence is a powerful novelist, but plans leave patterns that outlast luck. Our job is to track patterns without falling in love with them. 3i Atlas will tell us what it is by what it does when the power is highest and the wind is strongest. If it is a pretender, a few more weeks of sunlight will strip the mask. If it is a probe, the mask will turn out to be its face. Let us put the scary word on the table and take the teeth out of it. Weapon. Could a cloud of hydrogen cyanide drifting in space harm anyone on Earth? On its own, almost certainly not. Space is huge. Gas expands into vacuum and thins fast. By the time any cloud stretches across planetary distances, its concentration is so low that it becomes a tracer, not a toxin. Then there is the atmosphere. Incoming molecules are battered by sunlight, broken apart by chemistry, and burned by entry heating long before they could pool near the ground. Nature gives us dilution, dissociation, and distance as shields. So where does the fear come from? Delivery. If a thing can aim, time, and concentrate its emissions, the risk picture changes. Imagine a nozzle that does not breathe in all directions, but exhales along a narrow path. Imagine a release timed to intersect Earth's orbit when Earth is actually there. Imagine a burst that is not a mist, but a directed plume with a higher initial density. Now we are no longer talking about a passive cloud, but about trajectory math plus control. That is where the word weapon enters the chat. Start simple. To deliver anything in space, you need 3 ingredients. A way to change velocity, a way to know where your target will be, and enough energy to maintain the plan. Gas venting can provide the first. Even a gentle thrust, if held steady for days, can bend a path by meaningful amounts. Star trackers and known ephemerides can provide the second. The positions of Earth and the timing of its motion are not secrets. Solar power, rising toward perihelion, can provide the third. If there is intent, the recipe exists. Now, dial back the adrenaline and add physics. A plume launched at one moment will expand as it flies. The farther it travels, the thinner it gets, even if it was sharp at the source. Aiming a diffuse plume to intersect a moving planet is like trying to paint a line across a highway with a spray can from a mile away, while the wind changes every minute. You can try, but the world will fight you. The solar wind pushes on ions, radiation pressure pushes on dust, magnetic fields twist charged particles, the plume smears. There is also chemistry to respect. Hydrogen cyanide is fragile under harsh radiation. Ultraviolet light cracks it. Collisions with other particles chip it apart. By the time any survivor molecules approach the top of the atmosphere, they face another gauntlet of reactions. You would need a sustained series of releases, tuned to a schedule, to keep concentrations high enough to matter at altitude, and even then the odds of ground-level danger remain tiny. That is not comfort by denial, it is comfort by math. So why keep this hypothesis alive at all? Because delivery does not need to be lethal, to be strategic. A concentrated release aimed not at the ground, but at orbital infrastructure could still matter. Satellites are sensitive. Sensors can be blinded by unexpected gas and plasma. Surfaces can charge in odd ways. Communications can be disrupted by a temporary fog of ions. A well-timed plume through a busy orbital shell would be a nuisance at best, and a significant operational mess at worst. That is a more credible target than breathing humans. And there is a second angle that is not about poison as a weapon, but poison as a clue. If hydrogen cyanide appears as a byproduct of a power system or a thermal management cycle, then the sudden onset we saw might be less about aggression and more about activation. The exhaust of a machine tells you it is on, not what it plans to do next. In that reading, the gas is a status light, not a bullet. So here's a way to think with a cool head. We hold two frames at once. Frame 1 says, the cloud looks scary but behaves like a spill in the ocean. It spreads, thins, and becomes background. Frame 2 says a device could, in principle, sculpt emissions into narrow jets, use thrust to set up an intersection with vulnerable orbits, and create targeted interference. In the first frame, the threat to life on the ground is not credible. In the second frame, the threat to space hardware is plausible, but would leave fingerprints. Those fingerprints are within reach of our instruments, directional plumes that keep their aim through rotation, repeated releases that match predicted windows when Earth or high-value orbits cross a specific line in space, localized changes in satellite drag or charging that correlate with those windows, spectral features of fresh gas seen from multiple vantage points along a path rather than as a broad diffuse halo. If we see those, we rethink. If we do not, we relax. Could this all be a cosmic coincidence, or is something else going on? The honest answer is that the scariest version demands the most coordination and leaves the most evidence. The simplest version demands no plan at all and leaves almost none. Until the evidence points, we should refuse both panic and complacency. Curiosity first, measurement next, then judgment. Here is the promise we can make to each other as the clock runs toward perihelion. We will treat fear as a hypothesis, not as a conclusion. We will not give the word weapon-free rent in our heads. We will ask better questions. Is the gas directional? Is the timing strategic? Are the side effects on space weather measurable? If the answers line up, we escalate our concern with facts. If they do not, we retire the hypothesis with a nod and move on. Set the clock. Late November. 3I Atlas will reach perihelion, the nearest point to the Sun, in its current path. In comet life, this is the loudest chapter. Heat surges, gas escapes, dust lifts, tails grow long and bright. If the poison switch was the prologue, perihelion is the stress test. Will we see a smooth ramp like a normal comet, or a second clean step that looks like a plan? Perihelion matters for two simple reasons: power and camouflage. Power first. Solar energy rises fast as distance falls. If there is any technology on board, solar input becomes free fuel. Systems that were marginal at 2 astronomical units become robust near 1.5. Pumps run longer, valves cycle faster, guidance has headroom, camouflage second, natural comets flare exactly now. A machine that wanted to act without drawing attention would choose this window. Any strange jump in brightness can hide inside the fireworks we expect from real ice and dust. So what should we watch? In plain words, brightness is the first line on the whiteboard. A natural comet brightens along a curve that roughly tracks solar heating and the square of distance. There is noise on top of that, but the backbone is smooth. An engineered sequence could ride that curve and then jump in a way that does not fit the math. A staircase on top of a slope. If the light jumps abruptly and stays high without a matching change in dust, that is odd. If brightness swells with dust structures that expand like rings or shells, that is textbook. Tail geometry is the second check. Near perihelion, the solar wind is loud. Ion tails should snap away from the sunday. Dust tails should sweep back with a graceful curve. If we keep seeing a sunward spike that holds attitude while our viewing angle changes, the projection trick loses power. If that spike pulses on a rhythm that ignores the rotation period, it is even harder to pin on surface vents. A steady spike at a fixed angle smells like control. Gas mix is the third. As a comet warms, different ices take their turn. Water dominates closer in. Carbon monoxide and carbon dioxide play their parts. Hydrogen cyanide usually rides along but rarely leads the parade by itself. If the mix shifts toward the usual ladder, natural winds around. If hydrogen cyanide remains dominant while overall activity surges, we ask why a colder molecule still carries the show under hotter light. Non-gravitational acceleration is the fourth. Every vent pushes. The trick is to separate random puffing from persistent thrust. Track the orbit carefully through perihelion. If the path shows a small but steady nudge that lines up with a stable plume angle, that is not geology behaving. That is guidance. A random nucleus can still mimic thrust for a while, but it will drift as sources rotate and fade. Control prefers straight lines and repeatable vectors. Rotation coupling is the fifth. Many comets wear their spin on their sleeve. Brightness rises when an active region turns into the day side and falls when it returns to night. That heartbeat can be measured. If 3i Atlas shows a second rhythm that holds steady while the spin ticks by, you are looking at two metronomes in the same song. One belongs to daylight, the other belongs to intention. There is a weather report we cannot ignore. The sun itself is restless. This phase of the 11-year cycle brings more flares and gustier solar wind. That adds noise to our measurements, but also hands a device extra power and cover. A coronal mass ejection can scramble spectra, bend ion tails, and make faint plumes hard to read. It can also supply a burst of particles a machine could harvest. If something waits for the loudest moment to act, it will wait for a storm inside the perihelion window. Expect turbulence, plan for it. Do not let weather become an excuse for every sharp edge we see. This is also the moment when the public science machine can shine. Spectra from Mars orbit, from high mountaintop radio dishes, from optical observatories spread across longitudes, can create a time-stitched record of what actually happened at the peak. Short statements in real time, even with large error bars, are better than celebratory blur. The story is moving. The audience deserves motion pictures, not only after-action reports. What would calm the room? A brightening curve that follows the physics we teach in classrooms, a dust coma that grows fat and symmetrical, an ion tail that whips away from the sun without stubborn sunward features, a gas ladder that looks ordinary for the distance, a path that requires no extra thrust to explain. That picture lowers every pulse. What would escalate without drama? A light curve that jumps in steps, a persistent sunward spike that rides through changing geometry, a gas mix that stays skewed toward hydrogen cyanide under increasing heat, a measured nudge in the orbit that keeps pointing the same way. Show those together, and the device hypothesis graduates from a late-night question to a working model. Could this all be a cosmic coincidence? It could. Coincidence loves crowded plots. But perihelion is not just another scene. It is the scene with the lights turned up, where both stories are forced onto the same stage. Nature will look like nature. Design will look like decisions. Our job is to keep our eyes on the curves, not on our hopes. Count the nights, watch the tails, read the spectra, track the path. Then let the data pick the mask up or pull it off. Either way, we learn what we need to know. When a story threatens to run away with our imagination, we bring in a control. Meet Comet Swan, a bright, well-behaved traveller that did exactly what textbooks say a comet should do. It brightened smoothly as it neared the Sunday. Its coma swelled into a symmetrical haze. Its tail streamed away from the star, with the grace of a windsock in a steady gale. Place that picture next to 3i Atlas, and you can feel the difference before a single number appears. Start with brightness, the heartbeat most people notice first. Swan rose along a curve. That felt natural. Night after night, amateur telescopes picked up a steady climb, and professional instruments measured a clear relationship between distance and light. That is what solar heating does to ordinary ice and dust. 3i Atlas, by contrast, has spent much of its approach looking stubbornly modest while throwing off a gas signal that suggests it should be louder. If gas is plentiful but dust is shy, the light stays muted. Swan shouted with dust. Atlas whispers with gas. Now consider shape. Swan's coma grew plump, and even a bright cotton ball that faded gently into space. Under magnification, you could sometimes see shells and ripples that marched outward as the nucleus rotated and fresh patches caught sunlight. That is how a surface exposed to heat breathes. 3i Atlas often appears as a tight point with a thin, changeable halo, and on some nights, features that jut at odd angles. Instead of a fog bank rolling off the nucleus, you get puffs and spikes, as if the source were picky about where and when to vent. Tail physics teaches the cleanest lesson. Swan carried two signatures with textbook manners. Its ion tail pointed straight away from the sun, thin and blue in long exposures, uncurling exactly as the solar wind dictated. its dust tail arced gently back, broad and golden, the way sunlight pressure sculpts heavy grains that will not hurry. 3i Atlas complicates that picture. Reports of a sunward spike linger longer than a simple viewing trick should allow, and some nights the tail seems to hesitate or flicker. Swan obeyed the river. Atlas sometimes looks like it angles an oar. Timing seals the comparison. Swan's changes tracked rotation and distance in ways a student could graph. Brightness rose when active terrain rotated into day, fell when it slipped into night, and the overall level climbed as the sun grew larger in the sky. That rhythm is the signature of surface vents powered by dawn and dusk. Where 3i Atlas is concerned, we keep catching events that feel less tied to the clock on its skin, bursts that do not match an easy day and night cadence, features that hold a pose across spans when rotation should have twisted them. If the beat does not belong to spin, who is tapping the metronome? Chemistry adds another contrast without drowning us in jargon. Swan showed the classical ladder. Water, closer in. Carbon monoxide and carbon dioxide playing their expected parts. Trace gases along for the ride. With 3i Atlas, the dramatic entrance belongs to hydrogen cyanide, and it arrived early for the distance like a guest who did not read the invitation. If later spectra near perihelion show the ladder falling into line, the natural story breathes easier. If the mix stays skewed while activity rises, the control keeps raising an eyebrow. There is a fairness test we should pass before we judge. Not every comet is Swan. Variation is real. Some nuclei are darker, some carry less dust. Some rotate in complicated ways that make vents appear and vanish in odd patterns. Nature can be messy and still be natural. That is why the control case is a yardstick, not a verdict. We do not demand a perfect match. We ask whether the main beats line up. Smooth brightening, obedient tails, rotation-linked pulses, and a gas mix that evolves with heat. So we lay the frames side by side and read the differences aloud. Swan brightened on a curve. Atlas gave us a step, and then reluctance. Swan's tails behaved like flags in the wind. Atlas sometimes raised a lance toward the Sunday Swan's coma was a rounded lamp. Atlas often keeps its light in a tight fist. Swan's chemistry climbed the usual ladder. Atlas put a stranger on stage early and asked us to accept the billing. The pattern is not a smoking gun for anything engineered, but it is a reminder that our baseline exists for a reason. Deviations earn questions. Could this all be a cosmic coincidence? A noisy comet wearing unlucky geometry while we watch too closely? It could. Geometry plays tricks. Small bodies keep secrets. But comparisons are the backbone of science, because they force our eyes to stop drifting. Swan teaches the rules in a way any viewer can feel. 3i Atlas keeps bumping those rules with its shoulder. That friction is where the truth waits. Our next task is not to punish Atlas for being weird. It is to measure how weird, and to decide whether natural stacks can carry the weight. If they can, the control case will shepherd us back to calm. If they cannot, the contrast will give shape to a different story. Either way, Swan has done its job. It has reminded us what normal looks like, so we can recognize it when we do not see it. Before we chase machines through the dark, we owe nature a full hearing. Strange does not mean artificial. Many known effects can bend comet behavior into shapes that look engineered if you only see a slice of the dance. So we gather the natural stack and walk it in plain words, no jargon fog, just causes and the footprints they should leave. Start with fragmentation. Comet nuclei are fragile. Heat and spin can pry them apart. When a chunk splits, fresh ice faces the sun and gas shoots out fast. Brightness jumps. Jets appear from new edges. Dust can surge briefly, then settle as small pieces rotate and fall quiet. Fragmentation predicts companions in the halo, small points near the main body that drift slowly as gravity loosens its grip. It predicts sudden brightenings, followed by fading after the flash is spent. It predicts changing jet directions as the broken pieces tumble. If we see tiny shards marching away and brief flares that do not hold, fragmentation is a good fit. Now, rotation and vents. Even without breaking, a lumpy body with a few active patches can look like it has nozzles. When an active region turns into daylight, it hisses. When it turns away, it rests. That creates pulses. It also draws spirals and shells in the coma as dust is flung outward by spin. If vents cluster near a pole, plumes can keep similar angles across many turns, which mimics control for a while. This model predicts a heartbeat tied to a fixed rotation period, and geometric patterns that repeat like clockwork until sunlight reaches a new patch and the routine changes. Charged dust and the solar wind add another layer. The sun floods space with charged particles and a magnetic field. Dust grains that pick up charge can feel that field. In some conditions, the path of dust can kink, curl, or briefly point the wrong way before the solar wind irons it straight. This is messy but natural electromagnetism. It predicts short-lived features that depend strongly on solar weather. Sudden solar gusts should coincide with odd tail shapes. When the wind calms, the comet should return to textbook form. Non-gravitational forces from outgassing also deserve respect. When gas escapes, it pushes the nucleus gently in the opposite direction. Over weeks, a steady push can shift the orbit a little. This is not rare. Many comets show small path changes that modelers must include to fit observations. The test is alignment. Natural outgassing tends to track the day and night of the surface. The push direction wanders with the rotation and with which vents are most active. It should not point the same way for long unless the spin axis and the vent map cooperate by chance. There is also the thermal recoil idea often used to explain asteroid drifts. Sunlight warms surfaces unevenly, and re-radiated heat acts like a gentle thruster. For comets, this is usually drowned by gas jets, but near quiet phases it can matter. It predicts very small, very steady changes that correlate with spin axis and surface properties rather than with sudden vents. Put these together, and you can sketch a purely natural script for 3i Atlas. A crust cracks and a vent opens, delivering hydrogen cyanide sooner than usual because of a pocket composition that favored that molecule. Rotation modulates the output, drawing shells and making the tail flicker. A burst of solar wind bends the charged particles and gives us a sunward spike that lingers longer than expected because the viewing geometry is unlucky. Over weeks, the path shows a small nudge that changes with the orientation of the body, rather than staying fixed. Later, as the distance to the sun shrinks, water and other molecules surge, and the chemistry ladder falls into line. That story is not only plausible, it is elegant if the data lands where it should. So why are we still uneasy? Because the current list of facts strains that elegance at a few joints. The stair-step onset with no whisper before it. The persistence and prominence of a sunward feature that does not fade on schedule. The gas mix led by hydrogen cyanide at a distance where water often begins to take the crown. The modest dust despite strong gas, which keeps the light muted. The impression of clean angles in plumes, on some nights that hold a pose longer than rotation would prefer. None of these is fatal to nature. Together they ask for a very particular combination of cracks, spins, gusts, and viewpoints, all landing in the same short season. The honest move is to score it, not spin it. If fragmentation is real, we should identify companions in high-resolution frames and track them over nights. If rotation drives the show, we should measure a stable period and see brightness and jets follow that beat. If solar weather is the villain, tail oddities should correlate with specific flares and wind changes. If non-gravitational forces are in play, the direction of the orbital nudge should drift with the changing balance of day and night on the surface. And if we do not see those signatures after a focused hunt, the natural stack begins to wobble. That does not crown the device story by default, but it narrows the field. It gives the alternative a chance to compete on the same scoreboard. We are not married to mystery here. We are married to fit. The model that carries the weight of the evidence with fewer excuses wins, whether it wears ice or intent. Could this all be a cosmic coincidence? Yes. Coincidence writes many chapters in astronomy, but coincidence should shrink as data grows. Perihelion is our data engine. It will amplify the signals and expose the seams in both stories. Nature gets first right of refusal, as always. If it takes the case, we will hand it the file with relief. If it does not, we will keep the other folder open and keep asking the sky to speak plainly. When science touches public nerves, the problem is rarely the data. It is the delay. Space agencies collect light, turn it into numbers, and then decide how and when to talk. That decision carries weight. It can cool a room or set it on fire. With 3i Atlas, the room is already warm, which is why the pacing of announcements matters almost as much as the measurements themselves. Walk the pipeline in human steps. A sensor gathers photons. Engineers calibrate. Scientists subtract background, check pointing, and compare against reference stars. Teams run the same frames through independent reductions to make sure a single software path is not fooling them. Then come the internal seminars where people try to break the result before anyone outside sees it. All of this is healthy. The wider the audience, the higher the bar. The weight is supposed to be a safety rail. Now, layer in the real world of institutions. The National Aeronautics and Space Administration works with the European Space Agency, and with national observatories that answer to ministries, funding councils, and sometimes defense agencies. A Mars orbiter team cannot post every tempting plot the minute it arrives because other stakeholders care about how communications land. When a result looks ordinary, the path is straight. When a result looks like it might feed panic, the path bends. Every bend costs days, sometimes weeks. There is a cost on the other side of the ledger. Public trust is a budget, not a constant. If agencies post only applause frames and keep interesting spectra behind a long door, distrust compounds. People begin to read silence as strategy. They fill gaps with stories. In the age of citizen astronomy and global networks, that backfill spreads in hours. You cannot outpace it with a slow press cycle. The only antidote is intentional transparency that does not sacrifice rigor. What does intentional transparency look like in practice? Milestones and thresholds explained in plain language before the big window opens. Tell the public how many passes will be attempted. Tell them the minimum signal-to-noise required to call a line real. Tell them what bands are being searched and what a null result means. If a dataset is noisy, say it. If a schedule slips, give a reason and a new date, rather than the word soon. A 2-paragraph engineering note is more powerful than a glossy image when the mood is anxious. There are legitimate reasons to move carefully. If a spectrum hints at an unusual isotopic ratio, the team must be sure that the instrument did not shift a hair or that a calibration lamp did not age in a way that skews lines. If a feature appears in one set of passes and not in others, the team must rule out a pointing error or a solar weather event that changed the scene between looks. If a partner agency asks for quiet while they check their own data, courtesy and agreements matter. None of that is sinister. It is professional. But professionalism does not require opacity. A commitment to rolling updates would lower the temperature without lowering standards. Imagine a public log that says, Pass 1 was noisy, Pass 2 was better, Pass 3 reached the threshold for a first look, detailed ratios pending. Imagine a simple calendar that shows when instruments will try again and when a preliminary note will appear no matter what. That predictability lets the audience breathe. It keeps attention on the sky instead of on motives. There is also the question of who speaks and how. Scientists tend to prefer a single polished paper to 10 rough notes. That is admirable inside a journal culture. It is a liability in a live story, a brief, human voice that says, here is what we saw today, and here is what still bothers us, can carry more honesty than a week of silence. The habit of waiting until you can say everything pushes people to say nothing, and in a vacuum, rumor is king. The information economy around a mystery includes risk management. Officials worry about saying too much and being wrong. They should worry just as much about saying too little and being distrusted. The goal is not to feed hype. It is to give the public enough scaffolding to climb with you as the evidence improves. That is how you inoculate a community against both fear and overreach. You share the process, not just the punchline. So what would a better week look like as perihelion approaches? A short pre-window brief that outlines what will be measured and what would count as unusual. A standing promise that preliminary spectra will be posted within a day with clear caveats. A schedule for the full reduction. A note about how solar weather might complicate interpretation. A dedicated page that aggregates amateur observations with guidance on what helps and what does not. None of this decides the nature of 3i Atlas. All of it improves the conversation. Could this all be a cosmic coincidence where normal delays arrive at the worst time? It could. But coincidence is not an excuse to let silence grow thorns. Agencies can keep their standards and still speak early and often. If they do, the story will bend back towards science. If they do not, every gap will be read as a lockbox, and every lockbox will harden belief that something is being kept from view. 3i Atlas is an object in space. It is also a test of how 21st century science talks to a world that watches in real time. The measurements will decide the physics. The cadence will decide the temperature. Getting both right is part of the mission now. Energy shapes behavior. When power is plentiful, horizons expand. When power feels scarce, fear edits the script. That background noise matters because 3i Atlas is arriving in a decade when optimism about limitless energy flickers, and the patience for uncertainty runs thin. For years we were told the fusion dawn was close. Startups promised grid power soon, magnetic bottles stronger than anything built before, laser pulses stitched into starfire, investment spiked, headlines did too. Then the hard part arrived. Materials aged faster than expected, components ran hot, timelines slipped from this decade to the next. Analysis groups began publishing sober forecasts that many private fusion efforts would stall before full-scale plants. Hope met engineering, and engineering asked for more time. Why does that mood matter here? Because energy anxiety changes what stories people accept. When a society feels its future power is uncertain, it becomes more attentive to threats and more willing to fund defense. The same picture seen under a bright lamp looks like curiosity. Under a dim bulb, it looks like risk. 3i Atlas does not change when we worry about power, but our appetite for alarming interpretations can grow. There is also a tactical angle. If you believed an object in the inner solar system might one day threaten satellites or space infrastructure, you would move money now. You would fold new line items into budgets, orbital surveillance, hardening of networks, rapid response launch capability. Those moves have their own gravity. Once funded, they seek justification in fresh data. That does not make them wrong. It means incentives tilt the table. Perihelion slots into this timing like a gear. The highest solar input arrives as the fusion narrative cools and as nations reset priorities for the next fiscal year. Space is more militarized than it was a generation ago. Mega constellations carry internet and navigation. Weather models depend on fleets of sensors above the clouds. Every new worry in orbit ripples into commerce and policy. A strange comet in that environment is not just a curiosity. It is a policy question with line items attached. Now, turn the lens back to the object. If 3i Atlas were a device, it would also play the timing game. It would want power, it would want cover, it would wait for both to peak. That is one reason our checklist for perihelion matters so much. We must separate the natural surge of solar heating from any second switch that looks like a plan. It is easy to mistake the tide for intent when the tide is loud. There is a humane way to hold these tensions without falling into conspiracies. Admit that institutions have incentives. Admit that people inside them are mostly careful and well-meaning. Admit that public budgets and public fear can influence tone. Then keep asking for crisp data that survives those currents. A light curve is not partisan. A vector change in an orbit is not ideological. Ratios in a spectrum do not answer to a press office. Those are the guardrails. None of this lets us off the hook as viewers. Emotional energy is a currency too. If we spend all of it on outrage, we have none left for attention. The right stance is alert but not adrenalized. Demand regular updates. Reward clarity over drama. Notice when agencies post rough looks with honest caveats and give them credit for doing the harder, braver thing. That behavior is contagious inside institutions. If we want more of it, we have to notice and value it. The same goes for the private side of the sky. Citizen scientists and small observatories are already filling gaps with disciplined methods. They log exposures, share calibration frames, and check each other. That community can help dilute the distortions that money and mood can impose. Hundreds of small eyes make it harder for any single narrative to dominate. Data plotted across many longitudes and many instruments has a way of humbling stories that depend on one camera and one night. So we accept the timing as part of the weather. Energy debates will rise and fall, budgets will sway, commentators will find patterns in the tea leaves. 3i Atlas keeps moving regardless. The honest way to navigate is to discipline ourselves to the measurables. If perihelion brings a clean second switch, we log it. If the gas ladder falls into line and the tails behave like flags in the wind, we log that too. The energy mood outside the dome does not get a vote on what the photons say once they hit the detector. Could this all be a cosmic coincidence, with a strange visitor peaking exactly as our confidence in abundant power cools? It could. Coincidences happen, and they do not need a designer. The wiser response is to let the coincidence sharpen our focus, rather than tilt our judgment. When uncertainty is high, the cure is not louder claims, it is tighter measurements and a calmer voice. Perihelion is not just a heat test for an icy body, it is a clarity test for us. We will learn whether we can hold two truths at once. The world is tense, and incentives are real. The sky is indifferent, and evidence is king. Hold both, then watch what the light draws. Picture a thin, invisible fog that only wakes up under electricity. That is plasma, gas whose atoms have been stripped into charged pieces. In space, plasma is everywhere. The sun breathes it out. Meteors write it in the upper air when they burn. Spacecraft re-entering Earth ride inside a hot sheath that blocks radio for minutes. Ionized gas does not behave like the quiet air in your room. It bends radio, scatters light, and dances to magnetic fields. If 3i Atlas wears even a faint plasma veil, Much of what we see could be a mask. Start with brightness. Dust makes comets bright because it reflects sunlight, but dust inside an ionized envelope does not shine the same way. Charged particles can absorb and re-emit light at slightly shifted colors. They can smear sharp spectral lines into broader shoulders. They can change the polarization of scattered light, turning a clean glint into a muddy glow. To a telescope, that looks like a dim, stubborn coma, even when gas production is high. It matches the odd pair we already noticed: big gas numbers, modest light. Now consider shape. Magnetic fields do not push on neutral gas, but plasma is a passenger of fields. If the object generates or shapes a local field, even a weak one, ionized outflow can be guided like water in gutters. That can produce narrow spikes that hold angles, which is exactly what a nozzle would also do. The difference is intent. A field-guided plume could be natural if the nucleus carries a remnant field, or if the solar wind drapes its own field around the coma in a stable way. It could also be deliberate if a device shapes the field to hide or to steer. Communication blackouts hint at another effect. Radio waves hate dense plasma sheaths. They reflect, scatter, or die. If 3i Atlas wears a radio-noisy halo, some instruments might struggle to read clean signals through it, especially at certain frequencies. That would slow confident classification and make early spectra look inconsistent from pass to pass. The barcode of molecules would wobble until teams learned which bands slice through the fog best. From outside, that feels like a lockbox. Inside the lab, it feels like fighting noise. There is a stealth angle here that does not require malice. A plasma sheath can be a shield. It soaks up directed energy. It blurs sharp edges. It softens the radar signature of hard structures behind it. A natural coma does some of this already. An organized, field-shaped bubble would do it better. If 3i Atlas is a machine, a controllable sheath would protect it from micrometeoroids and from harsh solar gusts near perihelion. It would also explain why the object can vent strongly and still look visually shy. How would we catch a mask like that? Start with polarization. Dust scattering has a distinct polarization fingerprint that grows with distance from the nucleus in predictable ways. Plasma changes that fingerprint. If polarimetry maps show odd patterns or sudden flips that track solar wind changes rather than the geometry of dust, a sheath is likely. Then look at color. Ion emission has specific hues. If a sunward spike glows with the palette of ion lines, rather than the warm spread of dust, projection tricks lose power. Radio is another probe. Point a sensitive radio dish at a bright background source when the coma drifts across it. If the signal twinkles or fades in a way that reveals a layer of ionized gas crossing the beam, you have a direct measurement of the sheath's density and thickness. Do that at a few frequencies, and you can map how the fog blocks and bends. The same trick works at optical wavelengths as starlight flickers through a variable plasma screen. Spectral line behavior is a third test. Hydrogen cyanide and other molecules emit at well-known frequencies. A surrounding plasma can broaden those lines or skew them in ways that depend on electron density. If broadening increases when solar weather is rowdy and relaxes when the wind calms, that is a plasma thumbprint. If the line widths track only distance to the sun and stay smooth through storms, then the veil is thin or absent. Magnetism gives us a fourth handle. Even small magnetic fields can twist polarization and steer ion features. We do not carry magnetometers to the comet, but we can watch how ion structures respond when the interplanetary magnetic field flips direction during a solar sector crossing. Natural ion tails pivot. A field-shaped sheath might resist or pivot differently. If a sunward spike holds its pose through a known field flip, guidance, not draping, is doing the work. We should keep a natural path open. The solar wind can drape its field over any coma and create organized regions without help from internal machinery. Near perihelion, that drape can be strong and persistent. In that case, the mask is not disguise. It is weather. The test is consistency. Weather-driven structures should track the solar clock. Design structures should track internal timing, ignore rotation, and hold attitudes that make operational sense rather than meteorological sense. So, could a plasma veil be the reason a bright gas source looks like a dim light? Yes. Could the same veil carve narrow features that look like nozzles? Also yes. The difference between stealth and storm will come from how those features behave across changing wind, changing field, and changing viewpoint. A storm follows the Sunday. Stealth follows a plan. Perihelion is the perfect time to run these checks. The wind will shout, the field will twist, the light will rise. If we see polarization maps that jump with each gust, line widths that swell with each solar burp, and radio twinkles that come and go like weather, then the mask belongs to nature. If instead we see features that ignore the storm and keep time with a beat of their own, then the mask belongs to something that does not care what the sun wants. Imagine a field of small telescopes staring in unison, stitched together by a learning mind that never blinks. No committees, no coffee breaks. Just night after night of images rushing into racks of processors that decide, in seconds, what is ordinary and what is not. That is the new shape of astronomy. Autonomous arrays turning the sky into a live feed, where weirdness does not wait for a monthly meeting. If something behaves unlike nature, these systems will be the first to raise a hand. Machine learning, spelled out plainly, is pattern memory turned into prediction. Feed a system millions of images of normal stars, galaxies, comets, and satellites, and it learns the rhythms. Then give it tonight's frames, and it highlights deviations, a star that brightens too fast, a track that does not curve the way gravity says it should, a spectrum with a line where no line belongs. Humans can do this, but slowly. A machine can do it before you finish this paragraph. The power is not only speed, it is choreography. When an anomaly pings, the array can pivot, retarget, and gather follow-up data in minutes. Some systems are designed to split the load across wavelengths. One small telescope takes the color image, another focuses on narrow lines that reveal gas. A third watches brightness dance second by second, looking for high-frequency wiggles that betray rotation or pulsed jets. The result is a stack of evidence built while a human team would still be drafting an email to ask for time. So what could this teach us about 3i Atlas and objects like it? First, non-natural motion will not hide as easily. Subtle changes in trajectory that slip past tired eyes stand out to a classifier trained to expect Kepler's smooth curves. If a body keeps getting a tiny nudge that points in the same direction over many nights, the machine will notice the drift faster, flag it higher, and feed it into a model that asks whether outgassing could really do that. A natural push wanders with rotation. A guided push does not. The machine does not care which story is prettier. It cares which fit is tighter. Second, odd light curves will not die in inboxes. A comet that pulses at a beat not tied to spin looks like a drum someone is hitting. An autonomous pipeline can fold nights of data together, test 1,000 periods, and tell us whether a second metronome is present. If the pulse survives, changes in viewing angle, the probability of control climbs. If it fades when the geometry shifts, projection wins. The algorithm does the math without ego and posts the score. Third, spectral graffiti is harder to ignore. If an array is equipped with even modest spectrographs, it can build a rolling map of which molecules glow and when. If hydrogen cyanide stays high while water takes the stage, the system pushes that oddity up the queue. If line widths swell and shrink in sync with solar wind gusts, the plasma veil story gains traction. If lines hold steady through storms, the veil thins. These are decisions that used to take weeks. Now they can appear in dashboards before sunrise. Of course, a machine that never sleeps introduces a new question. Who decides what it can say out loud? Some arrays are public and post their alerts as they fire. Others sit inside agencies or universities with long review habits. The tension is obvious. Speed is useful when a comet is changing by the day. Discipline is useful when reputations and policy are in the balance. The answer cannot be silence. It must be a tiered voice. Immediate alerts marked as preliminary. Daily summaries that fold in cross-checks. Weekly reports that freeze the best numbers to date. Give the audience the layers. Let them choose the slice that matches their appetite for certainty. There is also a deeper shift under our feet. For a century, astronomy depended on patient people who stared and compared. Now, machines do the staring, and the first comparison. That is a gain, not a loss, if we use it to widen our field of view. We can aim the human mind where it shines, designing tests, finding biases, and telling the story with care. The machine is a scout, we are the cartographers. Could a device prefer to be seen by machines rather than by us? It is a delicious thought. A probe might hide its signatures in statistical patterns, too faint for casual eyes but obvious to a classifier that knows the night's baseline to 5 decimal places. If so, we are finally fluent in the right language to hear it. That does not mean every ping is profound. It means the silence between pings will shrink, and with it, the space for speculation to grow wild. There will be false alarms, a satellite glint misread as a plume, a bad pixel that writes a fake line, a gust of solar wind that makes a dust sheet look alive. The cure is not to slow down, it is to embrace redundancy. cross-check with different arrays at different longitudes. Compare instruments that see different colors and resolutions. Let disagreement be a feature, not a scandal. When three independent systems call the same odd beat, we listen harder. So what happens when the machine points at 3i Atlas and says, "Look again"? We do, fast. If the push in its path stays aligned with a steady plume, that is a headline. If the pulse in its light curve ignores its spin, that is another. If the gas mix refuses to climb the usual ladder at perihelion, that is a third. Stack them, and the story changes shape. Miss them, and we learn that nature can still fool the best scouts in the world and teach us humility in the process. The night sky is no longer a quiet canvas you visit once a month. It is a stream. The machine that never sleeps is our filter. It will not tell us what to believe. It will tell us where to look, sooner than we ever could on our own. If there is design hiding in the light, this is how we catch it. If there is only ice and sunlight and wind, this is how we prove it quickly and move on, wiser, for the chase. Open a drawer in an old observatory and you find glass. Hundreds of plates, each one a frozen night sky from a different decade. Now put those stars next to modern digital surveys and ask a rude question. Where did some of them go? A handful of pinpoints from the mid-century sky never show up again. Not dimmer, not moved, gone. Before we let our imaginations run, we clean the plates. Old emulsions are moody. Chemicals age, dust specks pretend to be stars. Cosmic rays splatter short streaks that masquerade as points if you blink. Teams who study this problem know the tricks. They cross-match plates from different telescopes, taken on different nights, at different exposure lengths. They throw out anything that does, not repeat. After the heavy filtering, a small residue remains, real-looking sources that appeared then and do not appear now. There is a sober stack of explanations. Some objects are dramatic variables. They flare for a night and then return to obscurity. Photometric calibration on historical plates is hard, so a tiny galaxy can present as a star on one plate if the sky was unusually crisp and the emulsion unusually kind. Gravitational lensing can brighten a distant source for a short time when a massive object drifts across the line of sight and focuses light for us. Add in the possibility of tiny tracking errors turned into dots by noise, and you can cover many cases without invoking anything strange. Yet the residue still nags. A few of the vanishing lights pass the boring tests. They appear on multiple plates and disappear across multiple modern surveys. They sit far from bright stars that might cause reflections. They glow with the roundness of a true point spread rather than the fuzzy edge of a blemish. If even a fraction of these are not artifacts, then our sky is more dynamic than the textbooks in your school locker ever admitted. So what could these be if they are not errors? The cautious answer is exotic but natural. Failed supernova events can flare briefly when a star attempts to explode and then chokes. Distant active galactic nuclei can flicker wildly and later go quiet below a survey's threshold. Dust clouds can stagger in front of objects and blot them out at some wavelengths while leaving others untouched. None of these need engineers. All of them could fit a few of the ghosts. Now, the more intriguing line. Suppose some vanishing points were never stars at all. Suppose they were local beacons or travelling probes holding a fixed pose against the distant background for a while. A patient device could sit in a stable orbit and shine with a steady brightness that makes it blend into the stellar wallpaper. Then, mission complete, it powers down, or moves on. The star you thought you saw was not a star. It was a light with an off switch. That idea does not ask you to believe in magic. It asks you to respect the limits of a plate from a century ago. Those plates could not measure parallax for faint dots the way modern missions can. They could not catch tiny proper motions over a few years. A disciplined mimic could fool every tool of that era. The modern remedy is straightforward. Return to those coordinates with modern eyes, not once, but many times, and across colours and wavelengths. Search for a faint remnant, search for a slow drift. If nothing comes back after deep exposures and long patience, put a small red flag there and look again in a year. Why does this matter for 3i Atlas? Because it resets our priors. If the sky hosts more transients than we assumed, if there are populations of short-lived or stealthy phenomena, then Atlas is not alone in being a puzzle. It is part of a larger pattern of things that appear, change, and vanish on human timescales. That does not prove Atlas is engineered. It does make the engineered hypothesis feel less like the only weird idea in the room. There is a practical crossover too. The same autonomous arrays that watch Atlas can scan the coordinates of vanished sources each clear night for a season. If one of those points winks back on, we will know within hours. If any shows a spectrum that looks like a lamp rather than a star, we will know soon after. The combination of long memory and fast machines is exactly what this problem needed. The glass drawers give us the map. The arrays give us the alarm clock. We should also guard against romantic temptation. A residue of stubborn cases is not a permission slip to rewrite physics. It is a permission slip to keep looking. Every time we dig into a mystery like this with better tools, nature hands us a new mechanism or confirms an old one, and the residue shrinks. The trick is to let the residue guide curiosity without letting it define the answer before the test. So here is a challenge we can accept together. Pick a small list of truly well-vetted vanishing lights. Publish the coordinates with the culling criteria. Invite the citizen astronomy world to join a long watch. If even one returns with a spectral signature that does not match any known class, the sky will have handed us a shout rather than a whisper. If none return, we will know that some ghosts belong to the chemistry of old glass and the drama of statistical outliers. Could this all be a cosmic coincidence? In one sense, yes. When you look at millions of points across decades, some will fool you. But the point is not to win an argument about ghosts. The point is to build a culture of long memory so that when something truly odd does enter and exit the stage, we catch it. 3i Atlas is on stage now. The vanishing lights remind us that the curtain can fall without warning. Let us keep the lights up and the notebooks open. Point an antenna at the sky, and you can listen all night. Build a stronger one, and you can hear the hiss of the Big Bang, the heartbeat of pulsars, the radar ping of planets. Listening is easy, talking is not. The rules change the moment you try to transmit. Suddenly you meet licenses, power caps, and a stack of forms that say, "Be careful." That difference is not an accident. It is policy drawn over a century of crowded airwaves. Here is the plain map. The spectrum is a shared street. Ambulances need lanes. Airplanes need lanes. Satellites need lanes. Astronomers guard quiet neighborhoods where faint cosmic signals can be heard without interference. The International Telecommunication Union divides the street and posts signs. National regulators enforce those signs. Most of the time this is boring and good. Your phone works. Weather satellites talk to Earth. Radio telescopes can hear hydrogen whisper from far away without a local station shouting over it. Now tilt the dish upward with intent. You want to send a message into deep space. You are no longer a harmless listener. You are a beacon. Regulators ask questions. How much power? Which frequency? Where is the beam pointed? For how long? The official answers circle around interference and safety. A powerful transmission can drown out other services if you are careless. It can cook electronics if you sweep across a satellite by mistake. So, the rulebook says, ask permission first. There is an unspoken layer that belongs in this story. If there is any chance someone is listening out there, a high-power message speaks for more than one person. It speaks for a town, a nation, a species. You can see why governments would want central control. Imagine a backyard array yelling in a band others use for navigation. Imagine a prank beam that looks like a challenge instead of a hello. The case for coordination writes itself. The price of coordination is that most of us do not get to talk. This is where the phrase radio silence enters with a sharper edge. We are not silent in any strict sense. Earth leaks radio and television and radar day and night. Those signals fade with distance, but they carry news of our presence into the local star bubble. Still, intentional deep space messaging is rare and usually goes through official channels with committees and caution. That caution can feel like secrecy when the public mood is already tense. It can also be the right instinct when the room is full of unknowns. So what does this have to do with 3i Atlas? If the object is engineered and if it listens, who speaks to it? Not you or me. The likely voices are the same antennas that talk to interplanetary probes. Those networks can whisper or shout. They can send narrow beams. They can hop frequencies. If any message was sent toward Atlas or if any response were detected, the first ears would be inside facilities that do not post to social media. That is not sinister by default. It is how spaceflight has worked for decades. It is also why a public protocol matters before the temperature rises. We can sketch that protocol in simple lines. First, a standing rule that no intentional signal aimed at a non-human object will be sent without public notice, and a brief delay for comment, except in time-critical safety cases. Second, a clear record of who decides and who can veto. Third, a pre-written set of messages that have been debated in the open so that we are not crafting our hello during a storm. Fourth, a promise to publish logs of any transmissions and any received signals as soon as basic checks confirm they are not instrument artifacts or known satellites. On the science side, keep the listening as wide and open as possible. Citizen radio arrays can scan bands that are safe to monitor and post their raw captures for cross-checks. Universities can host public dashboards that show when the big dishes are pointed near 3i Atlas and at what bands, without exposing anything operational that needs to stay quiet. The goal is not to crowd the control room, it is to crowdsource trust. There is a flip side too, responsible restraint. If you have a legal transmitter and a clever idea, now is not the moment to improvise contact experiments from your backyard. One bad headline can harden walls for a decade. The wise move is to push for transparent policy, rather than to dare the regulators to stop you. Curiosity is brave, discipline is braver. This is also the place to say the quiet thing aloud. Centralized control over transmission can be abused. It can hide mistakes. It can slow the release of news. It can let a small number of people decide what the rest of us are allowed to know. That risk is real. The cure is not anarchy on the air. The cure is bright process. Publish the rules. Publish the calendars. Publish the after-action notes. When the public can see the rails, they stop imagining traps. Could this all be a cosmic coincidence, with policy frictions landing on our path just as an interstellar visitor acts up? It could. The spectrum would be crowded with or without a mystery. The difference now is attention. People are watching the sky, and they are watching the way we talk about the sky. If we are careful and open, that attention turns into strength. If we are closed and coy, it turns into heat. So we keep our radio ears wide and our mouths disciplined. We ask for clear protocols and public logs. We resist the urge to shout into the dark just to prove we can. If 3i Atlas listens, we will hear it sooner together than alone. If it is only ice and wind, the same rules will make the next mystery easier to navigate with trust intact. Imagine an invisible predator drifting through the galaxy. No light, no glow, no warning. You only notice it when a background star briefly brightens, as if a cosmic magnifying glass slid across your view. That is gravitational microlensing, and it is how we catch rogue black holes, by the dent they press into space rather than by any light they make. One event, one brightening curve, then darkness again. If we can miss monsters that big, what else could slip past us until the geometry lines up just right? Here is the physics in plain words. Mass bends space. When a massive dark object passes in front of a distant star, the starlight follows curved paths around the lens. From Earth, we see the star slowly brighten, peak, and fade in a smooth, symmetric arc. No new color lines appear, no flicker from flares, just a clean light curve shaped only by gravity. Measure that curve carefully, and you can estimate the lens's mass and speed. Sometimes the answer is a planet. Sometimes it is a compact remnant. Sometimes it is a 12 solar mass shadow sliding through the Milky Way that we would never have known existed without this lucky alignment. Luck is the lesson. Microlensing only happens when 3 points, the dark lens, the far star, and us line up within a hair-thin angle. The odds at any one moment are tiny. So when we catch even a few events, it implies a hidden population. Tens of millions of black holes could be roaming the galaxy, most doing nothing dramatic, most invisible except for the rare nights when geometry betrays them. Absence of evidence is not evidence of absence. Sometimes it is evidence of invisibility. Now bring that humility back to 3i Atlas. We like to think our surveys have tamed the inner solar system. Arrays sweep the sky nightly. Software flags movers, catalogs expand. But our tools are tuned to find certain kinds of things: bright asteroids, dust-rich comets, objects that behave like they should under sunlight and gravity. Dormant bodies with dark skins and minimal outgassing are hard to spot until they wander close. Add in a taste for activation only at specific thresholds, and they can pass like submarines beneath the waves. We are good at catching fireworks. We are worse at catching quiet. The rogue gravity lesson talks about priors. If our galaxy casually hides stellar mass black holes, then our own neighborhood can hide smaller, stranger things. That does not make every odd comet a machine. It makes our confidence in completeness less cocky, which means we should design tests that do not assume the answer in their setup. Ask your instruments to be surprised. Give your algorithms permission to flag the unpretty and the faint. Microlensing also teaches discipline. The curves are unforgiving. You cannot bluff a black hole into existence with a noisy light curve. Either the brightening follows the math of a gravitational lens, or it does not. The same standard should govern our Atlas story. We should not accept a vague vibe of propulsion. We should look for a vector change that fits a sustained thrust. We should not accept a rumor of a sunward spike. We should track its length and brightness against viewing geometry and solar wind and see which equation wins. Extraordinary claims do not require poetry. They require fit. There is a second echo from the black hole hunt that matters here: timescale. Microlensing events can last weeks or months. Miss the beginning and your model weakens. Miss the fade and you may misjudge the mass. With Atlas, the perihelion window is our full light curve. The start, peak, and tail of this chapter will define which story survives. That argues for round-the-clock coverage, shared monitoring across longitudes, and a willingness to publish rough looks before the moment is gone. The sky does not pause for paperwork. Now, the psychological trap. Knowing we miss things can tilt minds toward paranoia. If there are unseen black holes everywhere, maybe every odd light is a predator. Resist that drift. The right response to hidden populations is not fear, it is better search. Build instruments that watch more of the sky more often. Teach them to notice deviations from expected motion and spectra without demanding a neat label in the first hour. Let surprise be a valid output. Curiosity, armed with cadence, beats anxiety armed with anecdotes. What does the rogue gravity lesson predict for Atlas in practical terms? First, expect that we may still be blind to parts of the behavior. Plan redundancy to catch what one instrument misses. Second, assume that a clean, quantifiable anomaly will be rare but decisive. If a small, steady, non-gravitational acceleration aligns with a persistent plume angle over many nights, that will stand out the way a lensing curve does. Third, treat null results with respect. If perihelion passes and every measurable falls inside natural bounds, let that calm carry weight. Nature deserves to win when it fits the data better. Could this all be a cosmic coincidence, with black hole stories merely reminding us the universe is unruly, while Atlas turns out ordinary? Yes, coincidence is plentiful at scale, but the moral is sturdier than that. Our detectors are brilliant but biased. The universe contains calm monsters and quiet machines, if any exist, that hide best by doing nothing until a trigger arrives. Our job is to build a surveillance of the sky that is patient enough and broad enough that triggers rarely catch us flat-footed. If we can weigh an invisible object from a fleeting brightening of a distant star, we can weigh the truth of Atlas from the shapes of its curves. Gravity gave us a method that does not care about stories. Let us extend that stubbornness. Measure, fit, falsify, repeat. When the light is this thin, every clean curve is gold. Imagine a pendulum that never slows down. No friction, no heat loss. Just a beat that keeps perfect time without spending fuel. That is the intuitive picture of a time crystal, a phase of matter that oscillates in a steady rhythm when driven, without drifting toward equilibrium the way everything else does. It sounds like science fiction. It is not. Teams have built them in quantum processors and in diamond at room temperature. Why does that matter here? Because if you wanted a probe to sleep for ages, wake cleanly, and run with ridiculous efficiency, this is the kind of physics you would covet. Let us strip the idea to bones. Normal crystals repeat in space. Salt and diamond are lattices, patterns of atoms on a grid. Time crystals repeat in time. When you poke them with a periodic drive, their internal state flips on a schedule that is not the same as the drive, and it does not fade. The system's oscillation becomes a clock that resists noise. In practice, a time crystal is engineered in a protected quantum system where disorder and clever driving keep the rhythm stable. The promise is not free energy. The promise is coherence that lasts. Translate that to a vehicle that must cross interstellar dark. Long missions punish batteries and moving parts. Clocks drift. Lubricants evaporate. Anything that can nap near zero and wake on a crisp cue is gold. A core that holds a protected oscillation could act as a master timer and a memory backbone, telling subsystems when to test, when to fire, when to vent, without bleeding energy to keep its place in line. The wake trigger could be tied to a simple external reference, the sun's brightness at a chosen distance so error does not accumulate over centuries. Wake at 2.1 astronomical units. Verify clocks. Move to mode 2. Where does hydrogen cyanide come in? If the internal power system is built around exotic chemistry or high-energy materials that require specific thermal regimes, the first wake step might be to purge lines, condition catalysts, and test small thrusters. The purge could produce hydrogen cyanide as a byproduct. The test could vent through fixed ports. From the outside, we would see exactly what is reported. Silence, then a clean spectral line, too abrupt for a warming curve, as a dormant system shakes off dust and proves it can breathe. There is another link between time crystals and behavior we can measure. A device that divides time into protected ticks would prefer to act in discrete sequences rather than on mushy ramps. You would expect steps, diagnostics that complete and hand off to the next stage, power rails that cross thresholds and unlock subsystems, a staircase, not a slope. Our light curves would reflect that personality. So would our spectra if gas releases happened in quantized bouts instead of continuous seepage. If you see bursts that recur with clock-like spacing that is not tied to rotation, you're listening to a metronome that lives inside the object, not on its surface. How could we test this without touching the thing? First, hunt for periodicity that survives geometry changes. Fold the light curve on many trial periods and ask whether a hidden beat appears, one that stays when the viewing angle shifts and when solar weather adds noise. Natural rotation will show up too, but a second, stubborn cadence that ignores daylight on the surface would be suspicious. Second, watch for discretized transitions in spectra. Do molecular ratios, change in jumps at repeatable intervals, as if valves were switching states. Third, track thermal behavior. A system that wakes subsystems in locked phases may show temperature plateaus rather than smooth warming. Detectable in infrared if the coma lets us see. There is a counter-story to respect. Time crystal research on Earth is young, fragile, and lives in carefully sheltered devices. Projecting that straight into an alien probe is a long leap. A clever natural nucleus could still produce bursts and steps as cracks open and close, or as rotation brings vents in and out of sunlight. The job is to separate a clock that rides the day from a clock that ignores it. Surface beats will drift as the spin state evolves and as active areas migrate. Internal beats will hold on through that drift, because they serve an itinerary, not a sunrise. Ask the uncomfortable question. Could a device with a protected internal clock coordinate a perihelion action that looks like a ritual? Wake, purge, power, orient, execute. Yes. Does that mean we should believe every step we see is the drum of an engineered heart? No. It means we should make the drum prove it keeps time when the room changes. There is one more tell: resilience. Time crystalline behavior is prized because it resists decoherence. A probe designed with that philosophy would be annoyingly stable. Plumes would hold angles. Output would recover to a baseline after gusts of solar wind. Diagnostics would repeat with little drift. Natural messiness has the opposite signature: paths that wander, beats that smear, vents that tire. So, could this all be a cosmic coincidence, with a cracked ice ball stumbling into sequences that look like a machine's ritual? It could. Coincidences love pattern-hungry brains. But if perihelion brings a second staircase, if gas pulses repeat on a beat that does not care about spin, and if small orbital nudges line up with those pulses, we will have more than a shape in clouds. We will have a clock that refuses to sit still, ticking not for us, but where we can hear it. Here is a tricky thought. What if the story around an object can be engineered even if the object itself is not? Could a rolling sequence of half-truths, slow releases, and dazzling visuals nudge millions toward a conclusion before the data is ready? People give this a dramatic name and wrap it in talk of staged invasions and holograms. Strip away the sci-fi, and you get a sober problem. Narrative can be weaponized. Uncertainty can be farmed. Start with the lever that moves crowds: expectation. For decades, officials waved off anything that smelled like visitors. Then, within a few years, we heard serious voices talk about unidentified aerial phenomena and new committees. That flip primed an audience to lean forward. When an interstellar object acts odd in the same decade, the timing feels scripted even if it is not. The mind loves arcs. Institutions rarely plot them. Coincidences breed stories. Could technology fake a sky event? Yes, within limits. Lasers can paint the upper air. Drone swarms can carry lights that dance. Digital compositing can fool eyes on a screen. None of that fools a spectrograph or a backyard telescope pointed at the right spot. A hologram in the clouds is theatre. A spectral line from a known molecule is physics. The cure for stage magic is a network of independent measurements that do not care about a press cycle. When light splits into wavelengths that match a lab lamp, you can embed it in any narrative you like, but the barcode will not change. Then, there is managed release. Agencies under pressure may hold data longer, not because of a puppet master, but because people fear being wrong in public. Delay plus vague language plus dramatic timing equals gasoline. Add a few viral posts that mix real plots with misleading overlays, and soon a simple telescope gap turns into a grand plan in the minds of millions. The problem is not that the public is gullible. The problem is that the cadence of truth is slow by design, while the cadence of rumor is immediate by default. So how do we stay sane without turning cynical? Build habits that force truth to surface quickly. Cross-check every strange claim against simple observables you can verify from multiple places. Did the line appear at the same wavelength on different instruments? Did the brightness jump show up in raw photometry from unconnected observers? Did the tail angle make sense across changing viewpoints? These are the questions that cut through narrative fog. If a claim fails them, you do not need to litigate motives. You can dismiss on method. There is a second, easier trap. Using the possibility of manipulation as a blanket to smother all uncomfortable data. That is convenient and wrong. A real anomaly does not become fake because it arrived at a dramatic moment, or because a clumsy press office made it sweeter. If 3i Atlas shows thrust aligned with a steady plume over many nights, that survives any conspiracy theory or public relations mistake. If it does not, that failure also survives. Reality is stubborn, that is our anchor. Now, for the honest assessment of the scary scenario. Could someone orchestrate a fear climb so that budgets swell and controls tighten? They could try. They would pick an object that many telescopes can see so the reality anchor holds even while the story bends. They would emphasize the weird beats and muffle the boring ones. They would taper data rather than dump it. The defense is not a counter-narrative. The defense is boring, relentless disclosure, daily spectra, light curves with timestamps, clear statements of instrument health. Invite amateurs and students into the data stream. That breaks the monopoly on interpretation. There is also the inverse danger, trying so hard to avoid the appearance of hype that institutions understate real risk. That is not honesty. It is fear of fear. If non-gravitational acceleration crosses a threshold that natural models struggle to carry, say it plainly with error bars. If a sunward feature tracks viewing angle exactly, say that too. If a perihelion jump does not fit the expected slope, post the plot. The audience can handle complexity. What it cannot handle is silence that lets rumor set the table and then invites science to defend desert. So where does that leave Bluebeam and other grand frames? As cautionary tales about psychology, not as default explanations for physics. They remind us that mass attention can be steered and that spectacular visuals can dazzle. They should not become an all-purpose solvent that dissolves inconvenient facts. When you feel the tug of a cinematic story, do the dull check. Ask which parts survive contact with independent instruments and which parts live only in edits and captions. The pieces that survive deserve your focus. The rest can fade without a fight. Could this all be a cosmic coincidence, with institutional stumbles and a moody comet arriving together to create a perfect storm of speculation? It could. Coincidence is cheaper than plots and happens far more often. The grown-up move is to be narrative-aware without becoming narrative-led. Use the chatter as a cue to look harder, not as a verdict in either direction. 3i Atlas will write its own ending in numbers. If it is ice and sunlight, the curves will say so. If it is guidance and thresholds, the curves will say that too. In both cases, the way we talk will matter for trust, but it will not change the barcode of a molecule or the vector of a push. Let the data lead, and the story will either keep up or fall away. We are down to 2 stories and a short calendar. The way out is a scorecard anyone can read. No secret math, no appeals to authority. Just a set of plain tests that, together, decide whether 3i Atlas is a messy chunk of ice or a controlled traveller with a plan. Here is how we watch without blinking, and how we let the data vote. Begin with the light. Plot brightness night by night through perihelion. Nature draws a curve. Design draws a staircase laid over that curve. If we see smooth growth that matches distance and sunlight, that is ice doing what ice does. If we see abrupt jumps that hold their new level without matching dust, increases, that is a mark in the device column. Ask yourself the simplest question: did the light glide or did it click? Now, tails. The ion tail should whip away from the sunday. The dust tail should sweep back in a curve. A persistent spike toward the sun can be a viewing trick for a short time. If that spike keeps its attitude while our angle changes, projection runs out of rope. Tie that observation to color. Ion features glow with a different palette than dust. If the sunward spike looks like ion light and defies the viewing geometry for days, the explanation is no longer a neat classroom diagram. It is something choosing an angle and keeping it. Chemistry is the barcode that does not care about mood. A natural coma near the sun is a water show with the usual supporting cast. Hydrogen cyanide is present, but not the conductor. If the mix shifts into that familiar ladder, breathe easier. If hydrogen cyanide keeps leading while the furnace gets hotter, ask why the cold guest still holds the microphone. Add one more check. Do molecular ratios change in jumps, as if valves are switching, or in gentle slopes, as if ices are simply warming? Steps speak. Motion is the ruthless judge. Outgassing can nudge a path. It cannot keep a steady, unblinking push in one direction unless the surface and spin axis cooperate by luck. Track the orbit nightly. If the fit demands a small, persistent acceleration that lines up with a steady plume angle over many rotations, call it what it looks like: thrust. If the nudge wanders with rotation as different vents wake and sleep, call it nature doing its untidy job. Spin beats are the stethoscope. Many comets wear their rotation as a heartbeat in the light curve. That is good. Measure it. Then listen for a second pulse that ignores day and night on the surface. Fold the data on trial periods and see what repeats. A machine loves a steady drum. A surface loves syncopation and drift. If two metronomes play at once, one tied to spin, one not, you are hearing geology and guidance in the same song. Weather can lie to you, so we check against it. Solar wind gusts and magnetic field flips will bend ion structures and broaden spectral lines. Map odd tail shapes and line widths against solar conditions. If the weirdness obeys the wind, chalk it up to weather. If it ignores the gusts, your culprit is closer to the nucleus. Polarization is the mask test. Dust scattering writes a predictable polarization pattern that grows with distance from the nucleus. Plasma smears and twists it. If polarimetry maps flip or warp in step with solar wind changes, then the mask belongs to nature. If they sit stubbornly in a configuration that makes operational sense rather than meteorological sense, then someone is shaping the veil. Cross-checks keep us honest. Look for the same beats across different instruments, different longitudes, and different colors. A pulse that survives 3 independent pipelines is real. A spike that appears only after heavy processing in one place is a mirage. Let the machines that never sleep do the first pass, then let humans beat on the results. Agreement is gold. Disagreement is a signal to look closer, not a license to declare victory. Finally, transparency. A daily slate of rough spectra, light curves with timestamps, and instrument health notes will cool the temperature faster than any press flourish. If agencies hit their promised cadence, rumors shrink. If they miss without explanation, silence becomes its own data point. So what would settle this quickly? A perihelion window that shows a smooth rise, obedient tails, a chemistry ladder that falls into line, nudges that wander with rotation, and no clock other than spin. That is a natural verdict with receipts. What would flip the table? A staircase on brightness, a sunward spike that ignores geometry, a gas mix that stays skewed under heat, a steady non-gravitational acceleration aligned with a fixed plume angle, and a second beat that keeps time through changes in view. Stack those, and the only honest sentence left begins with the word guidance. Could this all be a cosmic coincidence? A perfect storm of cracks, gusts, and unlucky camera angles? It could. Coincidence writes clever parodies, but coincidence has trouble keeping time for weeks. That is why we built the scorecard. Curves, angles, barcodes, vectors, beats. 5 pillars. If 3 or more lean the same way, the story is no longer a vibe, it is a verdict. We will keep our eyes on the numbers and our minds off the drama. If nature wins, it wins clean. If design shows its hand, it will show it in the only language the sky speaks: light and motion. Watch with us. The vote is about to be counted. We have walked the long spiral down to 2 simple doors. Behind one is ice that surprised us, then settled into physics we already teach. Behind the other is guidance thresholds, steady plumes, a second heartbeat that ignores daylight on the surface. We cannot vote with vibes, we can only vote with light and motion. So we end not with drama, but with a plan you can feel in your hands. First, the calendar. Perihelion is the crucible. Stack nightly brightness with timestamps and refuse to smooth away the truth. Did the light glide or did it click? That one graph will carry more weight than 1,000 hot takes. If it clicks without a matching surge in dust, mark the column that spells control. If it glides while dust swells like a lantern, sign the ledger for nature. Second, the angles. Watch the tails through changing geometry. Ions should whip away. Dust should sweep back. A sunward spike can be a projection for a while, not for days on end. If that spike, keeps its attitude while our viewpoint shifts. The trick is over and something is choosing a pose. Color seals it. Ion glow is a different palette than dust. Read the hues and let them choose the story. Third, the barcode. Molecules do not care about opinions. Near the sun, water leads a natural choir. Hydrogen cyanide sings backup. If cyanide keeps the microphone as heat rises, ask why. If ratios change in clean steps rather than lazy slopes, that is a valve switching, not a glacier thawing. Post spectra, early and often, with ugly error bars and plain caveats. The public can handle noise. Silence is the only frequency that always lies. Fourth, the vector. Fit the orbit through perihelion with and without a steady non-gravitational push. If the fit demands a small, persistent acceleration that points the same way while the body rotates, call it what it is: thrust. If the nudge wanders with the day and night of the surface, outgassing earns the credit, and the case for machinery shrinks. Fifth, the beats. Measure rotation. Then fold the light on trial periods until you either find a second pulse that refuses to drift or you do not. A metronome that stays on tempo while the spin goes by is a signature no storm can fake. If the only drum in the room is rotation, tip your hat to geology and close the other folder with relief. While we measure, we fix the way we talk. Agencies publish a rolling log that trades perfection for cadence. What did you point at? What was the health of the instrument? What did the first pass see? When do we get the next look? 2 paragraphs a day can diffuse a month of rumour. And when a plot is messy, say the quiet thing out loud. Messy is honest. It means the team is real. Citizen observers, this is your chapter too. Pair up across longitudes. Post raw photometry and calibration frames so others can reproduce your curves. Include the sky quality and the gear you used. It is easier to trust what we can redraw. If you have polarizing filters, or narrow band gear, map the coma's polarization and color. Small rigs multiplied across the world can beat one big scope that posts a week late. Educators and explainers teach the scorecard, not the speculation. Curves, angles, barcodes, vectors, beats, 5 pillars. If 3 lean the same way, call it with confidence. If they split the vote, teach what uncertainty looks like and why that is not failure. We do not worship doubt. We use it to keep our footing on slick ground. And yes, we plan for both doors. If nature wins, we celebrate a weird comet that taught us to upgrade our instincts and our instruments. We will have learned that plasma can wear masks, that geometry plays tricks longer than we thought, and that our new machine eyes can spot steps and pulses in real time. If guidance wins, we will have already laid the rails for the next moves. Ask before we transmit, harden the orbital shell, accelerate sky coverage, and open data, and build an international tabletop exercise for a future encounter so we do not improvise policy at midnight. So where do we put our fear? In a box labeled to be opened only by evidence. Fear cannot plot a trajectory or split a spectral line. It can only shout. Curiosity, by contrast, writes code, schedules, telescopes, and fills notebooks with numbers that do not care how we feel. Choose curiosity. It ages better. Here is the last thing that matters. You are part of the instrument now. Attention is a resource. Aim it. Do not reward theatrics that arrive without plots or timestamps. Do reward the hard, boring graphs that decide the vote. Share those. Mirror those. Help build a culture where truth travels as fast as rumor, because thousands of us carry it. 2 doors, ice or intention. Either way, the universe stays beautiful and strange. Either way, we get smarter if we watch with discipline. Stay with us through perihelion. Watch the curves, read the barcodes, track the vector, listen for the beat that does or does not exist. When the vote is counted, we will say the sentence the data demands together, in daylight, with the whole world watching.